Welcome back to Industrial Automation course, Lecture 11, Programming Function Blocks, Subroutines in Codesys. Today's topics are as follows: creating function blocks FB in Codesys, using return instruction inside the FB, creating global variables, using jump and label instructions, commenting the code in Codesys, using SR function block, and finally using RTC real-time clock function block. Video tutorials. Selected video tutorials from YouTube. Please watch the following YouTubes. These are supplementary materials to this lecture course. So if you want to know more how to basically cover the topic of this lecture in a structured text or ladder logic, please watch these videos. So these are supplementary videos that help you to increase and enhance your skills. Function blocks FB in Codesys. The aim is to implement the example in page 183 of the textbook. It is the materials conveyor system with a flashing light as a subroutine. So here we already developed and explained this example before. This is a conveyor and there is a weight sensor here. This is a pilot light. Okay, so when the weight goes beyond the limit and the sensor becomes activated, then the pilot light should start flashing. Here we have a subroutine for flashing the light with two on-time timer, and this is the main program part. Here we have the subroutine. So we want to see how we could implement a subroutine in Codesys or a function block in Codesys. Creating a new project. In order to create a FB in Codesys, right-click on Application, Add Object, and POI. Select function block and specify its name, flashing. Okay, so once you selected the function block here, you could also give it a name, flashing. In the corresponding program window, you will see the variable declaration area here. Okay, so we have the main program and we have our function block or subroutine, which we name it flashing. So you could see all the variables here. There are var input and var output areas to determine the input and output variables. Okay, so we have three areas basically: var input, var output, and general variables. Okay, and we could basically place our variables between the var and end for each of these types. Insert two TON blocks and create the flashing function. Okay, so these are on timers, and we already have how we could place timers and use timers. Be careful, we are in the flashing. We are in the flashing programming environment, not the main program. So once you do so, the Codesys automatically will declare the variables. And we name our timers TON0 and TON1, but it's up to you to choose any other names. You see that the var input and var outputs are still empty, but in the general variables, we have these two variables. Now, in the main program, you can try to develop the program and insert the flashing FB. You can drag and drop the FB from the POUs section. So here, it's the main program. Okay, so if you go to the POUs, yes, in the toolbox, you will see the flashing function block. You could drag it and drop it here. Okay, but since the flashing now at this moment doesn't have any input variables and output variables, see what will happen. However, as soon as you do so, the sensor contact will disappear. Okay, so it already drag and drop here, and the sensor disappeared, and only the FB will appear in the first rung. You will be asked to declare the new variable corresponding to the FB. In this way, the FB will be executed without considering the effect of sensor contact. So now we could declare a new variable flashing 0. So the type of the variable is flashing. And once we click OK, it should appear here in the list of variables for the main program. So why the sensor disappeared? Because flashing at this moment doesn't accept any input or output. So it cannot be attached to any other contacts. To control the execution of the FB by the sensor contact, we need to determine an input contact for the flashing FB. Okay, so let's back to variable declaration form of flashing, and we need to define an input. So here we have a start. We insert one contact, Boolean contact start here, and we'll declare this start in the var input. Okay, so it basically will be created automatically in the var section, but what you need to do, you need to move it to the var input section. In flashing FB, insert the contact at the first rung, namely the start. In the variable definition, move the start variable to var input area. Okay, now flashing could accept one Boolean input and could be attached to the sensor. In the main program, insert the sensor contact and the flashing FB. This time, the contact will be used as the input of the FB. The state of start contact inside the FB will be the same as the state of sensor in the main program. So whatever is the state of the sensor, then the state of the start in the flashing program will be the same, okay? Now insert a second rung with the sensor contact. In order to make it normally close, you can click on the negation icon, Ctrl+N in the toolbar. Okay, so here in the main program, second rung, we could put sensor and negate. We could negate it. Okay, you could either press this one or Ctrl+N to negate or contact. You could use the negation for a contact and for the coil. So negation could be used for both of contacts and coils. Okay, so you see where is the icon here. Add a coil to represent the pilot lamp, PL, here. Okay, so basically what we are doing, we are just implementing the program presented at the first page of this example, or the example of the book. Yes, so we are following exactly the same program. We want to implement the same program. Pay attention that since the TOM block are local variables inside the FB, you do not have access to the output of the timers. Therefore, you cannot assign it to the contact directly. You can see only the input and output variables of the FB. Okay, so here we want to have access to TOM variables, TOM.Q, but we can't because the TOM or any other variables are not defined as an output of the flashing subroutine. We don't have access to those. We need to change our flashing function block program. To have access to the output of the timer located inside the FP, one way is to create an output variable in the FP. So here, the output variable, and assign that variable to the input of the first timer. Move the declare variable to the var out section. So here we have a flash out is connected to the Q bit of the TON0, and once we basically declare this one, it will be listed under the variable list here. What we need to do, we need to move it to the var out because we want to have access to this variable outside FP. Now you can assign the contact to the output variable of the FP. So here now, once we click it in the list of flashing one, we could see flash out variable. So we could have access to this one, yes, as well as the start, and we use that the start for the input. So how we could differentiate between the input and output, start is basically a contact inside the FP and flash out is a coil. So this one is output and this one will be input. Okay, so we managed to accomplish first two rounds of the main program. Complete the program, run and test it. So the rest of the program is quite easy. You had it, it's basically a combination of contacts and coils. What you need to do, you need to follow the same basically program schemes that we had in the first page of the example, and you could accomplish your program. Okay, so this is a complete program. Do it by yourself in Codesys and try it out. Using global variables in function blocks. Another way of having access to the output of the timer located inside the FP is to declare it as a global variable, which can be accessed by all the POUs in the program. To declare the global variable, you need to add global variable list. Okay, so in the application, click on application, add object. Okay, so this is quite the same path for the visualization and POUs, yes, but now we want to choose global variable list. Okay, so we click on this. Specify a name for your global variable list and declare the TON in the list. Okay, so here in the global variable, you see tab, we could see all the global variables. Now we need to just basically declare the TON here in the list. In the FP program, change the associated variable for the first timer to the one declared in the global variable. So we want to replace this ton0, which is a local variable, by a ton2, which is a global variable. In the main program, change the associated variable for the contact in parallel with the negated sensor contact with the output of the timer declared in the GLV. So here, what we need to do, we need to replace the output variable of the function block by the global variable, okay? We don't have to do this. It's just basically an alternative solution to the output variable, and we could use the global variable here. Run the program and check the functionality, okay? So check it in the visualization for both of the cases. Check it in visualization, you will see better how the program works. Return instruction inside function block FP in Codesys. You can also use the return instruction inside the FP in order to finish the execution of FP at a certain rung. Insert a new rung with a contact to condition the return and insert a return instruction. So here in flashing subroutine, we could have a new rung, okay, and place return. How could we place return here? This is an icon, okay, and we could use this icon to place return here. Insert another rung in order to test the operation of the return instruction. Run the program and check the operation of return. Okay, so this is only for testing. The subroutine should never reach this rung. Okay, so this rung must not be implemented. Okay, so it's just basically redundant rung here, but check the performance of the program to see if the return function works properly. Jump instruction in Codesys. The aim is to implement the example in page 180 of the textbook. We want to show how the jump instruction works and how we can implement it in Codesys. Okay, so we have 3 pilot light, push button, and switch. And we already discussed this program, I believe, in previous slides. We want just to see how the jump works. Okay. So once the switch is true, the jump will be activated and we will skip this rung tree. Okay, so the rung tree won't be implemented once the switch is true. Okay, we want to see how we could implement it in Codesys. Jump instruction in Codesys. Start implementing the program in rung 2. Insert a jump instruction and name it label 01. Okay, so here we have, or basically we want to place the jump instruction here or label 01. Okay, how could we do that? In toolbox, jump, drag and drop it here and name it label 01. In rung 4, right-click on the left side and insert a label 1, rename it as label 01. Okay, so right-click here, then you will see this window, and choose Insert Label, and select label 01, or rename it to label 01. Run the program and check the functionality of jump. Check the state of all the outputs in different situations. So you want to be sure that the program will skip rung 3 in certain conditions. You can also insert the label by clicking on Insert Label icon. Name it label01. Run the program and check the functionality of jump. Check the state of all the outputs in different situations. Okay, so here you basically select drawing 4 and press on this icon here, and then name it label 01. We already had jump label 01, so it will be associated to this jump. Commenting parts of code in Codesys. Similar to other programming languages, it's possible to provide comments of the users in the program. You can also use commenting one or more runs with the purpose of debugging. Now, we want to make the running tree of the program as a comment. Select the run and click on the toggle network comment state icon in the toolbar. Here is the icon in the toolbar, okay? Or Control O, you could also use Control O. Choose basically the run you want to comment. Press Control and click on O, or use this basically icon here. Accordingly, the color of the code in running tree will change. Okay, so you will see different color and you will understand that, okay, so this part is commented, is not going to be executed, and it's very good basically technique for debugging. It means that this run will not be executed. Run the program and check the functionality of commenting. Okay, so always have your Codesys open, program it step by step, and check the functionality of the program and see how you could basically use these labels. Using SR function in Codesys, SR block in Codesys is similar to the SR flip-flop. Can set and reset the state of the output by providing commands at the input of the block. Now we want to generate a pulse train using the SR block. Start by inserting a box in the program. Okay, so we want to create the pulse train using SR instruction. We start by placing the box. Select the SR block from the library. So click here to define what type of the basically box is this. And under standard, select SR, set reset. Declare the SR0 variable. As you notice, two inputs are inserted for the block. Okay, so once you do so, you will see set and reset and output. We need to set the output whenever it's not set. Okay, so this is basically for creating a pulse, and we are using SR0.Q. So what is Q1? Q1 is the output, and at the beginning Q1 is false, and we're using negated value for the set, so it becomes true. Okay, so we could set it. For the reset, we'll use SR0.Q. So the state of the set and reset will be always opposite of each other. Okay, so at the beginning Q1 is false, so this coil here will be true, and then we could set it. Once we set it, Q1 becomes true, and once it becomes true, then we will set it automatically, and this cycle basically continue. Okay, so we could have a pulse train. Run the program and check the functionality of SR function block. Repeat the experiment with RS function block. What is the difference? Okay, so I'm going to leave that to you to investigate and see what would be the difference between this R and RS block. Using RTC instruction in Codesys, RTC, runtime clock instruction, returns the current date and time, starting at a given or preset date and time. So here we have the inputs, outputs of RTC blocks. RTC instruction can be used to keep track of the amount of time a process have been operating. Okay, so in a structure test, we have enable bit, we have PDT, okay, or predefined time, we have output, and we have CDT, okay? And CDT is elapsed since PDT, okay? So date and time elapsed since PDT, okay? And it's somehow similar to the retentive timer, okay? And we could basically keep track of the amount of time process have been operating. Very similar. This aspect of RTC is very similar to retentive timers, I could say. Okay. Okay, so let's see how we could use RTC instruction in Codesys. Insert a start contact and then a box in the program. Select RTC from input assistant window. Okay, so once you click here, you could basically under miscellaneous, here you could find RTC. Declare the RTC0 variable. Once you do so, you have enable bit queue, PDT, and CDT. Okay, so this is a predefined time, and this is elapsed time after PDT. Using RTC instruction in Codesys, determine a preset date and time like this format. So the first part will be date and second part will be time. Okay. Save and run the program. When enable bit is false, the CDT output is by default 1970 year. Okay, so basically it starts by default from this year. Okay. As soon as EN goes through, the timer will start timing, and you can see the current date and time. Okay, so once the start becomes true, DT will be exactly at the beginning, same as PDT. CDT will be same as PDT. Okay, and then will increase relative to the PDT. Note that output Q follows input EN. So Q is true once the EN is true. This function block provides the functionality of the example in page 165 of the textbook for monitoring the time. Exercise. Write a program in which you can turn on a motor using a start push button and turn it off using a start push button at any time. Keep track of the amount of time for which the motor has been in the run mode. In case the time is more than a given time or value, 1 hour, 30 minutes, and 20 seconds, turn on a pilot lamp. Okay, you could also use a retentive timer for this case. Exercise. Implement the traffic light control system shown as a function which takes the preset time of the timers as input parameters. So here we have preset values for these timers. For example, this one 30, 25, 5 years, 25. We have these preset time values. We want to have a function that accepts these inputs. Then call the function in the main program providing the same values shown in the figure as the inputs. Okay, so we want to be able to change the preset time value of these timers by the function. Okay, so the function should accept these values as input. So please do these exercises and submit them to Moodle.